When we look at half-lives, which will be our last kind of example of kinetics so far this week, these are typically first-order processes. And the question we ask is how long until we have half of our original amount? And interestingly, many half-lives are constant in their degradation, as in it takes exactly the same amount of time for us to lose half of our product, so going from 1 to 0.5, and then the same amount of time from 0.5 to 0.25, another half of it. So these are typically first-order processes. And the most common one you're probably used to hearing is radioactive decay, in which half of your sample degrades in a certain amount of time, and then another half of it degrades in another equal amount of time. That's not to say that, you go from 1 to 1/2, you go from 1 to 1/2 for one half-life, and then half of that amount, which will be 1/4, will be your second half-life. And then half of that, which will be 1/8, for your third half-life. And so we ask ourselves, how long will it take, what's our half-life, for this to be, for our concentration at that number, our half-life, to be half of our original concentration? So we might plug that into our formula for first-order kinetics. And if we do so, we get that ln of 1/2 is equal to the negative k of your half-life, which is t1/2. t1/2 is your half-life. It's, again, that specific amount of time for half of your substance to decay. And if we go ahead and rearrange this, we see that our half-life is equal to negative 0.693, which is the natural log of 1/2 over k. And so we can use this, again, this is for first-order kinetics, to solve things. We might say, I have, it takes 10.2 days for my uranium sample to decay to decay by half. What is the rate constant? Thankfully, this is a pretty easy equation for us, right? We have our half-life and we have our constant. That's all we can do. And next we'll look at the reverse of this. So if it's 10.2 days, that's our half-life. So we simply need to plug that in. 10.2 days is equal to negative 0.693 over k. And if we go ahead and switch things around, we're going to get negative 0.693 divided by 10.2. And we get that k is going to be, again, since this is a decay process here, we will have that, I'm sorry, the negative shouldn't be there. I lied to you. The negative becomes a positive because the natural log of half is a negative number, so that negative actually goes away. I was thinking k needs to be positive. So doing so, we get a 0.0679. Interestingly enough, this will be inverse days. So our unit is a little bit different here. We could convert that to inverse seconds if we really wanted to, but it's just showing you what you can do with this equation. We could also take a rate constant that we know and see what the half-life is going to be. For example, at 510 degrees Celsius, our first order reaction, that's important here, is, we can figure that out. If k is 6.8 times 10 to the negative 4 inverse seconds, what's the half-life? It's nice when I get to use the same data set for a bunch of different examples. It makes it easy on me. Simply, we need to put the t half, time of half-life, is 0.693 over 6.8 times 10 to the negative 4 inverse seconds. Go ahead and plug it in, 0.693 divided by 6.8 times 10 to the negative 4. and we get 1019 seconds, which if with 6.2 really becomes 1.0 times 10 to the 3 seconds. So, hooray! We have completed our half-life. So it's about 1,000 seconds for half of this reactant to react. And so that's our last one for this week. Next week we'll look at temperature effects, as well as the actual mechanism information we get by doing kinetics. And finally we'll look at catalysis and how the presence of certain things within our reactions can help them to proceed faster. Have fun and enjoy kinetics.